we're going to cover domain and range. You'll see several examples of horizontal and vertical asymptotes. I'm also going to explain the difference between using brackets and parentheses when you write the answer to the domain and range. You can use the timestamps to skip around, skip ahead. You could skip this intro. I'm going to keep speaking for a little bit longer. Each of the answers will be presented to you right below me. In the box below me, you'll see the domain and the range box. And then in the bottom left, during a given example, you're going to see that example's animation on a loop. And you might be able to make sense of the domain and the range just by looking at that video on loop. But I will break down the example slowly in the main window here. Now I am going to go slow. I am going to be detailed. I'm going to be very repetitive. So you can skip around using the timestamps, or you could put the playback speed on double to get through it a little bit faster. In the description, you're going to find a PDF of all 16 graphs. We're doing 16 examples. So I would encourage you to either print that out or put it on a tablet and follow along. Write the answers down. Write down the answers before I reveal them. Try these on your own. Right? Because it's easy to think that you understand it when I'm sitting here explaining it to you. But the real question is, will you be able to reproduce this on your own? Also in the description, you're going to find a link to the Desmos graph that I used to create these animations. So you can see, I know it's technically not code, I don't know what else to call it, but you can see all the code that I typed into Desmos to make these animations. You can see the actual functions that I typed in to get these graphs. And so if that inspires you, if that's something you want to try to figure out, that's there for you as well. Also, we are not finding the domain and range from the equation of a function. That would require algebra. We're not going to do any algebra in this video. We're only going to find the domain and range from the graph of a function. So a little bit of a difference there. Here you only have to understand how to look at it graphically. We're not going to do anything. We're not going to write anything down. We're not going to solve anything. So should be straightforward, but I hope this helps. I hope you learn something. Again, feel free to use those timestamps to skip around. Here, we'll get started. Here's example 1. We'll go ahead and pull it up on the main grapher. So here, again, I don't care what type of function this is. All I care about, here's the graph. We're going to find the domain and range just from looking at the graph. So to find the domain, you want to scan this graph with a vertical line from left to right. This is what you should visualize when you're looking at your homework or your paper or whatever. We're coming from the left. We first make contact with this graph at -5. Now, I only care about the x coordinate. I don't care that the y coordinate here happens to be -1. For domain, we only care about the x coordinate. So let's see where this graph ends. If we continue scanning across this graph, where is this graph going to reach the end on the right? And that's going to be at 5. So what we've done here is we've boxed this graph in on the left and on the right between -5 and 5. We've created boundaries for it. That's another way you could think of it. We've boxed it in. Good. Another thing we need to pay attention to as we work through these examples is, does the graph make contact with its boundaries? So looking over here on the left boundary, does the white graph actually make contact with the blue boundary? And the answer is yes. In fact, if I click on the white graph, Desmos is going to produce a little gray dot right here, and I can press that. And we get our point. And because there's a solid point there, that means we've made contact. What about the right? If I look over here, you can see that little gray point as well. I can click that, and we see that it actually makes contact with 5. I don't care about the 4 right now. We only care about the 5. So why do I bring this up? Well, when you write the answer to this, and the domain here is going to be -5 to 5, when we write that, you need to write it using brackets, and we use brackets when it makes contact, and you'll see that right below here. There we go. We got our domain. Brackets because it makes contact. Good. Range is going to be the same thing, but instead of scanning from left to right, we're going to come up from the bottom and scan up. So coming up from the bottom with a horizontal line, we'll first make contact with this graph down here at -5. And now I'm referencing the y coordinate. I don't care that the x coordinate down here happens to be -1. I care about the -5. We continue scanning up until we reach the top of the graph. So go ahead, think for yourself, when am I going to reach the top of this graph? And if you thought 4, you are correct. So good. We now have this function boxed in on the bottom and the top. So we have left to answer the question, does this graph make contact with its boundaries? And you can see up here, if I click and press, we get a point there. We do make contact with that 4 up there. How about down here? How about down here? This one may not be as obvious. When a graph bottoms out like this, the minimum will make contact with the boundary. And I've already done this, but if you click this, Desmos will generate that point, meaning it makes contact, it touches the boundary. So our range here is going to be a bottom of -5 to a top of +4. And because it makes contact on the bottom and the top, we will write this with brackets, just like you see below. All right, good. So there's the domain and range of example 1. Here's example 2, a little more involved, but this is a good one. So coming from the left, we'll first make contact with this graph at -6. And this closed dot here is a bit redundant. It is just communicating that this does make contact with the boundary. So we're going to use a bracket on that -6, but let's go ahead and continue, and we're going to scan across this until we reach the right end of this graph. And that's going to be over here at 7. But what we'll see over here at this 7 is an open dot. Let's talk about that. This open dot is trying to communicate something to you, and that is that the graph does not make contact with the boundary. That is, it gets infinitely close to it, but it will never make contact. So this boundary is at 7, but the graph itself never gets there. So the graph will reach 6.9. It'll reach 6.99. It'll reach 6.99999, as many 9s as you could possibly imagine, just not infinite. But it will never touch 7 itself. So kind of a weird idea here, but it gets infinitely close without even touching, without ever touching. So we've boxed this function in, we've boxed this graph in on the left and the right between -6 and 7. It touches at -6, but it doesn't touch at 7. So when we write the interval from -6 to 7, we're going to put a bracket on the 6 and a parenthesis on the 7. So that's what that looks like. To find the range, we're going to come from the bottom. And we first make contact with this graph at -4. It has a minimum at -4 down here. And those minimums will actually touch the boundary, right? I could click that. You're going to get a dot. There's your -4. Don't worry about the x coordinate. It's just how this one ended up working here. So good. Let's keep scanning up. We'll scan up to the top of this graph. Where's the maximum of this graph? What do you think? Well, the maximum is at +4. And it does make contact. There's a dot. So our range here is from -4 to 4. It makes contact with -4. It makes contact with +4 up top. So the range here is going to use brackets on both sides, just like this. We've got it boxed in, above and below. Good, so here's the domain and range of this graph. If you want to see what function I typed in to get this, click on that Desmos link below. Example 3 is a semicircle. And we're going to come from the left here. I don't want to say we first make contact with this graph at -2 because we don't make contact. Rather, we've gotten as close to the graph as we can get without touching. And that's because of this open dot. Again, this open dot is communicating that the graph doesn't actually make contact with the boundary. It gets infinitely close, meaning this graph will touch -1.9. It'll touch -1.9999, as many 9s as you could think of, but it's not going to touch that -2. It won't make contact. So infinitely close without touching, kind of a crazy idea here. But anyways, continue scanning across till we reach the other side, and we lose contact with this graph immediately at 6. So because of this open dot on the right as well, this graph will touch 5.9, it'll touch 5.99, it'll touch 5.99999, but it's never going to make contact with that 6. So when we write the domain here is -2 to 6, but because of the open circles, we don't make contact and we communicate that with parentheses. So we're going to write -2 to 6 with parentheses. There's your boxed in animation. Let's switch to range. Coming up from the bottom here, we are going to not make contact with this graph at -3, but that's as close as we can get without making contact, without touching. There's a little more to this, but that's okay. Continue scanning up. Where's the top of this function? Where's the maximum here? That's going to be up here at 1. Now, you don't see an open dot here. This is a maximum. Maximums do make contact with the boundary. If I go over here and I click, Desmos will give me that point, meaning it makes contact. So it doesn't make contact on the bottom because of these open dots, but it does make contact at the top. So we boxed it in between -3 and 1, but we're going to put a parenthesis on the -3 and a bracket on the 1 like this. So good. This is the domain and range of example 3. Example 4 has the first asymptote we've seen in this video, and we'll get there in a minute, but first let's go ahead and come from the left. We first make contact with this graph at -6, and we do make contact with the boundary, so we'll use a bracket on that -6. And scanning across, we're going to go until we immediately lose contact with this graph, and that happens at 5. So what we have right here at x equals 5 is a vertical asymptote, and an asymptote is a line, a boundary, that the graph will get infinitely close to without ever touching, kind of like the open dots we've had so far, but it behaves a little bit differently. This function, this graph, is going to shoot up and again get infinitely close without ever touching that boundary at 5. Now, if we go up here, let's go all the way up to 100. And you may think, well, I don't see the white line anymore. It looks like it's buried underneath the boundary, and that would kind of be synonymous with it making contact with that boundary. Well, if you think they're making contact, it's just because you haven't zoomed in enough. So here's where you really get a good visual on these asymptotes. Is if I start zooming in, we will eventually see that white line reappear, and a gap will start to form. And here it is. If you don't see a gap, it's just because you haven't zoomed in far enough. And here's what's crazy is if you notice right here at the bottom of the screen, you can see very faintly here below that each of these main grid lines is, let's see, 10 hundred thousandths, 10 thousandths, 100 thousandths, is 1/100,000th of a unit. So we're talking about very small gaps here, and even smaller still, smaller than you could possibly imagine. And that's how these behave. So again, this graph will get infinitely close to 5. That is 4.9, 4.99, 4.99999, as many as you could think of without ever touching. And so to communicate that in our answer, we put a parenthesis. So a bracket on the -6, right? Did already show the boxed in animation. We got a box in between -6 and 5, making contact with the -6, but not making contact with the 5. So here's how you write that. -6 to 5, bracket on the left, parenthesis on the right. For the range, we'll come up from the bottom, and we first make contact with this graph at -3. And let's go ahead, let's see if we can find an upper boundary for this graph. And it may initially look like, oh, no, here we go, we can see it right here. We did not get on top of this graph. You can see the graph breaking out of the box right here. So maybe we just need to go a little bit higher. What if we push up a little bit higher? Well, now we've contained everything that's on the screen, but you got to be able to think beyond the graph. If I zoom out, we see that this graph breaks out of our boundary, breaks out of our box. It keeps going up. So we could try to keep going. We could try to get on top of this. But what you'll see here is this graph extends up forever. You'll never be able to get on top of this, no matter how high you go. So here's the first of this type that we've seen today as well. We do have it bounded on the bottom at -3, making contact. but there's no upper boundary. It goes on forever to infinity. And so the way we're going to write this is bracket on the -3, comma, infinity. And we always use parentheses on infinity because you can't really contain it. But anyways, so there you go. You got a vertical asymptote. You got an infinite boundary, which doesn't exactly make sense. But there you go. That's example 4. Here, you're going to have a vertical and a horizontal asymptote, and one of each of those will be in the domain and range. But starting with domain, we'll come from the left until we get as close to this graph without touching, and that's at -6. So what you have right here is a vertical asymptote. In the previous example, the function went up. Now it's going down. That's okay. It doesn't matter. The point here is that if it looks like the graph has made contact with the boundary, it's just because you haven't zoomed in enough. So if we zoom in here, you're eventually going to see that white graph reappear, and there will be a gap between the graph and the asymptote, which is the boundary. So we're going to need a parenthesis on -6, and we'll keep scanning to the left until we reach the end of this graph. And we may try to, but what you'll notice here is the graph breaks out of the boundary we have so far. So maybe we just need to extend our boundary a little bit. And if we do that, we'll go ahead and see now we've contained everything that's visible to us. But again, you have to think beyond the graph. If it looks like the function keeps going, you could probably assume that it does. So if we zoom out, there it is right there. It breaks out of our boundary. We can try to keep going, we could try to contain it, but this function, this graph, is going to extend infinitely to the right, no boundary. So we've only got it contained on the left at -6. There's an asymptote there, so we want a parenthesis on the -6. It goes to infinity, which also uses parentheses. Here's the domain as an interval, -6 to infinity with parentheses. To find the range, we'll come up from the bottom, but what you'll notice is we're already in the range of this graph. So I'm just going to go to the top of this graph, which is at 4. And we see here that it's asymptotic. We got a horizontal asymptote at y equals 4. We could go over here and try to find a place where it makes contact with the boundary. I'm over here at 100 now. But if you think it's making contact, just zoom in and you will see there's a gap. That's what asymptotes do. That's how they behave. So let's go ahead and try to get underneath this graph. We've gotten on top of it. Is it possible to get underneath it? We'll scan down here, backwards of what we've been doing, but same idea. And we'll see down here that we break out of our boundary. So we could try to go a little bit more. And we've contained everything that we can see. But if we zoom out, we'll notice that it breaks out again. And you're never going to be able to box this in on the bottom. You'll never be able to get underneath this graph. So it has no boundary below. It has a boundary above at y equals 4. So we're going to need you still got to write your answer from bottom to top. So bottom here is -infinity to the top of 4, and they'll both use parentheses. Whenever you have an asymptote involved, you're going to have infinities involved. Sometimes it may be positive, sometimes it may be negative, but those two things go together. I have this example titled The Misleading Asymptote, and you're going to learn something here in that graphs can cross horizontal asymptotes, but more on that in a minute. Let's start coming from the left, and we get as close to this graph without making contact. That is, we've bounded it in on the left at -3. Now we do have an open dot here, right? So that means that this graph doesn't actually make contact with -3. It gets infinitely close without touching. Now let's scan across and try to find a right boundary for this. And we'll come out here to 8, but we'll see that our graph pokes out of the boundary a little bit. So if we go a little bit more, we can bound everything that we see. But think beyond the graph. If I zoom out, you're going to see here that the graph breaks out of our boundary, our box here. So we can keep going. We could try to get on the right of this graph, but it's impossible because this graph does go on forever. So the domain here, we've got it boxed in on the left at -3, but you can't box it in on the right. So our domain is -3 to infinity, both parentheses. Now for the range here, we scan from bottom to top. I'm going to go ahead and go straight to the top here because there's a point that I want to make. There's a maximum here at 4, and maximums do touch their boundaries. And I'm going to start scanning down. And we're going to lose contact with this graph on the right side at 1. Meaning we have this horizontal asymptote here, which if I only showed you this much of the graph, it would appear as though we've bounded the graph below. And again, this is an asymptote, so if you zoom in there, you're going to see that gap. But what's interesting here is even though it doesn't touch over here or anywhere to the right, we do have the graph crossing out of this boundary right here. We have it contained at this little piece. And because of that, we need to keep going. We need to keep scanning down until we get to the bottom of every part of this graph, which here happens at -2. So actually, let's back that up because I do want to make this statement. Does this graph have a horizontal asymptote? Yes. Does it also cross its horizontal asymptote? Yes. Right? So this is kind of this is an important truth here, is that graphs will not cross their vertical asymptotes. That's impossible. But it is possible for a function, the graph of a function, to cross one of its horizontal asymptotes. As long as it's still, well, not as long, but it will still have its asymptotic behavior if you go far enough to the right or far enough to the left. But there may be some place in the middle here where it does cross. So that is worth knowing. We've contained this graph on the bottom and the top between -2 and 4. We have an open dot on -2. We have contact at the 4, so we put a parenthesis on the -2 and a bracket on the 4. Coming from the left, we're already in the domain of this graph. We'll come to the right boundary, which is at 6 with an open dot, meaning this graph gets infinitely close to 6 without touching 6. It will not touch the 6. And let's go ahead and scan backwards here, see if we can't get a left boundary on this graph. We'll come out to the edge of our screen, and we see that we have not contained it, right? This graph does escape our boundary. So maybe we just need to go a little bit more. We can go a little bit more, extend our boundary a little bit more, and we've contained everything that we can see. But think beyond the graph. If we zoom out just a little bit, we see that we will break out of this boundary. So you could keep playing this game, extend it a little bit more, then zoom back out, extend it a little bit more, then zoom back out. If you think you've contained this graph, you just haven't zoomed out enough. So there is no boundary on the left. We only have it contained on the right at that 6. So left to right, that's going to be -infinity to 6, parentheses all around on that answer. For the range, we'll come up from the bottom and we get as close as we can without touching at -4 because of that open dot. Let's go ahead and try to get an upper boundary. So scanning up, we will, where did I go to? I went up to 4. And so, yes, we are above this graph. It appears that we've contained it. But if you zoom out, you'll see that our graph breaks out of our upper bound. So we could try to go more, right? Go ahead, extend that upper boundary a little bit more and see if we can get on top. So we've gotten on top of it again. at least what we can see. But if we zoom out, there you go, it breaks out again. So it's just this back and forth game. If you get on top of it, just zoom out and you'll see that you haven't contained it. So this function, it's a square root function, by the way, and it is extending infinitely to the left. We already got that in the domain with the negative infinity, but it's also extending infinitely up. Mind you, it's not going up as fast as it's going left, but it will go up and left forever. So we've only have this thing contained on the bottom by -4, but we can't contain it on the top. So this is -4 to infinity with parentheses for the range. Coming from the left, we hit a vertical asymptote at -5. You may be thinking, well, there's a gap there. There's a pretty obvious gap right there. Can't we get a little bit closer? And the answer is no, right? Because if you go far enough up and you move over just a little bit, you're going to be making contact with the graph. So we have to maintain that gap, and it starts at -5. Good, we're going to go to the end of this graph. Where's that going to be? That's going to be at 6. Now we do have a closed dot here, and the closed dot is redundant. I could remove the closed dot and it would mean the same thing. So if I haven't said that yet in this video, no dot implies closed dot. So whether I have a dot at the end or not, both imply contact with the boundary. So we don't have contact at the -5, but we do have contact at the 6. So we're contained here. We're contained between -5 and 6, parenthesis on the -5, bracket on the 6. Coming up from the bottom, we first make contact at -5. That is a minimum, so that makes contact with the boundary. And then let's try to find an upper boundary. We go up until, where did I go? 6 here. So we can see we're breaking out of our upper boundary. We do not have this thing contained. We could try to go a little bit more, and don't be fooled. Yes, we've contained everything on the screen, but if we zoom out, we can see that it breaks out of this boundary. It doesn't matter how high you go, how high you extend your boundary, you're never going to get on top of this function. We've only contained it below at -5. So the range here is -5 brackets to infinity parenthesis. All right, example 9, we're halfway through. This example is titled the first union. So I'm going to teach you what a union symbol is, and that is when you need more than one interval to write the answer to the domain or range. So far, all the examples, the answers have been single intervals, but that's not always going to be the case. In fact, from this example, for the rest of the video, we're going to be using multiple intervals to express domains and ranges. So, but same idea, come from the left here until we make contact at -2, and that does make contact, so we'll use a bracket on that -2. But what you'll notice here is if we're scanning across, we lose contact before we reach the end. So obviously there's more graph to the right here, but we have this place in the middle where we lose contact with the graph, and that's because we have a vertical asymptote, but this time it's not at one of the ends, it's going right up the middle of this graph. So let's look at this. I know we've looked at this many times, but this one's unique. Let's go up to 100 and zoom in. This time it's not just one-sided. You have graph to the left and to the right of the asymptote, both the same distance. There's that same equal gap, and they will never touch that asymptote. So we have this gap 2, the number 2, x equals 2, is not in the domain of this function. So let's write an interval for just that much. We have -2 to 2, contact on the -2, an asymptote on the 2, so that's going to be bracket -2 to 2, parenthesis. And now, we're not done. There's still more to this graph, so we need to put a union symbol. Here's what I'm teaching you. This is the new thing. We're going to put a union symbol after that interval and continue. Let's go until we reach the final end of this graph, which is at 6, making contact. So We've boxed this graph in between -2 and 6, but this time we have a gap in the middle. For the left part, we've already written that interval. Let's write the interval for the right part. For the right, we have 2 to 6, but parenthesis on the 2, bracket on the 6, right? Because we don't make contact at 2 because it's an asymptote, but we do make contact at 6, so we put a bracket. So that's the domain here, and it requires 2 intervals to express it. Let's do the range now. Coming up from the bottom, we first make contact at -3. And we do make contact. There's no asymptote this time. And we continue moving up. We're going to try to find an upper boundary for this graph. We can see that 6 is not enough. We went up to 6, but the graph extends beyond 6. So let's go a little bit more and see if we can't get above this thing. And we've seen this many times today. You're not going to be able to get on top of this thing. This graph does not have an upper boundary. It extends infinitely up. So we have our lower boundary down here at -3. It extends up to infinity. So we write that bracket -3, comma, infinity, parenthesis. Good. So another thing I want to point out here. Just because the domain had a gap and required 2 intervals does not mean that the range will require 2 intervals. The range here could be expressed with 1 interval. In fact, you will see throughout the remaining examples that the amount of intervals required by the domain and the amount of intervals required by the range are completely independent. One may be 2, the other may be 1. It could be whatever, mix and match. But anyways, you'll see more of those coming up. Coming from the left, we're already in the domain of this function, but we lose contact with the function briefly at -1. Now, it's not the end of this function. There's still more graph on the right, but here in the middle, we're not in the domain. And this is a vertical asymptote. So let's go ahead and write an interval for this first half. We just came from -infinity, right? If I zoom out, you see that this graph extends infinitely to the left. So we're coming from the left. That's -infinity up to -1. We don't touch that -1 because it's an asymptote, so we need parentheses all the way around on this. That's the first part of this domain. We're going to put a union symbol before we write the second part. Continue scanning to the left. We'll try to to the right. We'll try to find a right boundary for this. And you'll find that no matter how far you go, the graph extends infinitely to the right, just like it did to the left. So there's no left boundary, there's no right boundary, there's just this gap in the middle, there's this vertical asymptote in the middle. So the second half of the domain here is -1 to infinity with parentheses. Same thing's going to happen with the range here. If we come up from the bottom, we're already in the range of this graph, but we have a gap, we have a horizontal asymptote at 1. So the first part of our range is -infinity up to 1 with parentheses, because we're not touching. And then we're going to put a union symbol. Put a union symbol for the second half. Continue scanning up. We could try to get on top of this graph, but again, it goes up forever. It doesn't matter how high you go up, there's no upper boundary here. So the second half of our range is starting at that asymptote, 1 up to infinity, with parentheses all the way around. So good, now you've seen an example where both the domain and range required 2 intervals each. That's a possibility. Okay, so we're going to keep going with multiple intervals for our answers. We have a bigger gap here for the domain though. So coming from the left, we are already in the domain of this function because it extends infinitely to the left, but we reach a vertical asymptote at -1. So it doesn't touch the -1. Let's write an interval for that, coming from -infinity on the left up to -1 on the right without touching. So that's parentheses. Now there's a whole other piece of this graph over here, so we're going to need a union symbol. And let's keep going. Let's keep going. We're gonna cover this whole gap. There's no graph in this gap between -1 to 2. There's nothing. The graph starts again at +2. Now let's look at this down here. This may be the first time we've seen something like this. This is not an asymptote. It may look like it, but it's impossible for a function to be asymptotic if it doesn't extend to infinity or negative infinity. This graph has an end right down here at 2. I want the x coordinate for domain. Meaning if I keep zooming, I can keep zooming in here and there won't be a gap. There's never going to be a gap here. I could keep going. You're never going to find a gap there. That does actually make contact with the boundary at 2. So that's going to need a bracket. Let's continue scanning to the right. And you already know where this is going, right? This graph extends infinitely to the right as well as the left. So you're not going to get a left boundary. You're not going to have a right boundary. You just have this gap in the middle. And in the previous examples, the gap was one number, one asymptote. But here we have a full interval that's empty. So we write the rest of our answer just with an interval for the right portion of this graph, which starts at 2, makes contact, doesn't have an end, goes to infinity. So bracket on the 2, parenthesis on the infinity, that's your domain. Good. Oh, here's your little... We have it squeezed in the middle right there. And then range coming up from the bottom will first make contact with this graph down here at the -5. And that does make contact. Continue scanning up. We hit a vertical asymptote at -3. So this is the gap in the range. The gap in the domain here was multiple numbers, multiple values. It spanned, well, 3 units, -1 to 2. But here, this asymptote is just a single value. There's only a gap at -3. So let's write an interval. We have contact at -5, but we lose contact at -3. So that's bracket -5, -3, parenthesis, union. Let's get the rest of it. Continue moving up. We will try to find an upper boundary for this graph, but there isn't one. If you zoom out, you will see that this graph keeps going up forever. So let's write the second interval, starting with the asymptote at -3, going up to infinity. So that's -3 to infinity, parentheses all around on that one. We have the bottom boundary at -5, no upper boundary. Coming from the left, we'll hit our first vertical asymptote at -6. Continue going until we hit our second vertical asymptote at -2. So here's the first piece of our domain, the first piece of our graph from -6 to -2. Because both of those are asymptotes, the graph will not make contact. We use parentheses for that interval, -6 to -2. Put a union symbol. Let's get our second interval. Keep going. We hit a third vertical asymptote at +2. So in the middle here, we go from -2 to +2 with asymptotes. So use parentheses for that. So our middle interval is -2 to 2. Put a union symbol. And let's go for a third interval. We reach our fourth vertical asymptote at +6. So our third interval is from 2 to 6 with parentheses. And that completes the domain. So we have this graph boxed in on the left and the right between -6 and 6, but we also have 2 vertical asymptotes that happen throughout this graph's domain. So we need 3 intervals to write the answer. For the range, coming up from the bottom, we're already in the range of this graph, and we reach our first maximum, if you will, at -1. So there's no lower boundary. We just came up from infinity, but we top off temporarily at this -1. Now, this is not an asymptote. This is a boundary. We make contact with this boundary, and we can even click the points, right? Desmos does have those points available for you. Let's write an interval for that. We just came up from -infinity and we stopped at 1, or -1, but we made contact. So we're going to put a bracket on the -1. Parentheses always on negative and positive infinities. Always, always. Let's go ahead and clear this gap. We reconnect with the graph here at +1, and we can get that point there. We are making contact. This is not an asymptote. It is making contact. And let's keep going. Let's try to get an upper boundary here. If we extend our graph up, we can cover everything that we see, but if we zoom out, we'll notice that this graph does go up forever. There's no upper boundary. You're never going to get on top of it. So the interval for the top portion of this graph starts at 1, making contact. So that's a bracket 1 all the way up to infinity with a parenthesis and a union symbol in between. So we don't have an upper or lower bound, but we do have this gap in the middle, meaning that our answer required 2 intervals for the range. So hopefully what you're noticing now is there's no pattern between how many intervals the domain has and how many intervals the range has. It could be whatever, mix and match. Here, the domain was 3 intervals, the range was only 2. Okay, example 13. This is our first piecewise example. So things are getting a little bit serious now. All piecewise means is that this functions in pieces. If you click on that Desmos link I have in the description and you go look at the functions that I type in, you will see that this required 2 pieces. So coming from the left, we first make contact with -6. Because that's a closed dot, that implies contact. We'll continue scanning until we reach an end of the current piece of this function, which is at -2. Now that's an open dot, so we don't actually touch -2. So we're going to need parentheses on that. So let's start there. We've got -6 to -2, contact on the -6, no contact on the -2. Put a union symbol. We'll clear this gap. There's no function here in the middle from -2 to +2. And then we find ourselves at an open dot at +2, so that will be a parenthesis. We'll continue scanning across until we reach the final end of this graph at the right boundary at 6, and that has a closed dot. So we need 2 to 6, parenthesis on the 2, bracket on the 6, just like this. So cool. This graph has multiple boundaries. If we can see that here, we kind of have each piece boxed in on the left and the right. Because we have these 2 pieces, we have the 2 intervals in our answer. That's pretty straightforward. For the range, okay, this is cool. Coming up from the bottom, we're going to make contact or get as close without making contact at -4 because of the open dot. And now you may be suspecting, right? It feels like the range should have a gap in it because the domain had a gap in it. But if we keep going up, if we go up here, we don't lose contact with the graph, not even there, but finally all the way up at 5. So the range here is a single interval from -4 to 5, parenthesis on the -4, bracket on the 5. So again, just because the domain has a gap doesn't mean the range is going to have a gap. Here's our second piecewise example. This one has some nice symmetry to it. Coming from the left, we're already in the domain of this function, but we reach an end to it, not the complete end, but the first stop at -1. This is not an asymptote. It does make contact with the boundary. So for this right portion, this goes infinitely to the left, so that's -infinity up to -1, but we make contact with -1. So parenthesis on the -infinity, bracket on the -1. Let's throw in a union symbol there. We'll clear this gap. There's no graph from -1 to 1, but we regain contact at 1, and it does make contact, this graph, right? If I click on this, Desmos will produce a point, right? No dot implies closed dot, which means contact. So use a bracket. And then we'll continue going to the right. Continuing to the right, we will try to get on the left of this. And again, it looks like we've contained everything on our window, but if we zoom out, we see that this graph does keep going. It's broken out of containment here. It extends beyond the boundary. So we could try to keep extending our boundary, but we're never going to find an end to this graph on the right. So the second part of the interval here, starting at 1 with a bracket, parenthesis, all the way to infinity with a parenthesis on infinity, bracket on the 1. Good. So we don't have a left or a right boundary, but we do have this gap in the middle. There's the domain. For the range, coming up from the bottom, we will discover a horizontal asymptote at -4. And again, asymptote means that no matter how far you go, if you zoom in enough, you will always find a gap between the graph and the asymptote. So it's never going to make contact, but that's as close as we could get without making contact. That's -4. Continue moving up. We will reach it's called a relative maximum of this graph. It stops temporarily here at -1, and it does make contact. So our lower bound here is -4, no contact. Our upper bound for this portion is -1 with contact. So parenthesis on the -4, bracket on the -1. Union will clear this gap. There's no range for this gap between -1 and 1. We regain contact at +1. Keep going. And then we hit our second horizontal asymptote at +4. So we have multiple upper bounds and lower bounds here on these two pieces. We have each of these pieces boxed in. That upper piece is from 1 to 4. So here's the interval for that. There you go. There's the complete range. So this one, again, this was a very nice graph. This had some nice symmetry to it. You had 2 intervals for your domain, and you had 2 intervals for your range with gaps in between those. This is our third piecewise example, and this is a great example of how ridiculous piecewise functions could be. I mean, you could get as creative with this as you want. But let's take it one part at a time. We'll come from the left, first making contact at -7. However, we're not really making contact because it's an open dot, so we're going to want a parenthesis there. And continuing moving to the right, something happens right here. We have a bit of a jump. We have a closed dot down here, but we have an open dot up here. So this is the first time we've seen something like this in this video. Because this function has at least one closed dot, actually it has to have exactly one closed dot to be a function, this function is defined. There is no gap here. In fact, it's like a perfect handoff. The bottom defines the function at -3, and then the top takes over immediately after -3. So this is not a gap in the domain. It's most definitely not an asymptote. That's not even a possibility here. It basically means we didn't have to stop here. We didn't have to make a stop. So let's keep going until we reach the next place of interest. And that would be right here where we have 2 open dots. And here you go. This means that this function is not defined at +3. This piece does not define it, neither does this piece. So there is a gap here. So this right here, this is our first interval. Even though it looks like there's 2 pieces and there should be 2 intervals, this can all be written as a single interval from -7 parenthesis to +3 parenthesis because of the open dots. So that's the first part of our domain. We'll stick a union and keep going. Scanning again to the right, scanning more to the right, we will cover everything that we can see. But again, if we zoom out a little bit, it will reveal that this graph keeps going to the right. We broke out of our boundary, so we could try to go a little bit more, but it keeps extending. And if we zoom out, we'll see this graph for what it really is. This line goes forever to the right, so there's no right boundary. It extends infinitely to the right. So we just have to pick it up right here, which was at 3, parenthesis 3 to infinity. That completes our domain. So we have it bounded on the left at -7. We have a gap at 3, but then we have no right boundary. It goes to infinity. So just 2 intervals there. Even though we can see 3 distinct parts of this graph, the domain can be expressed with just 2 intervals. Let's see about the range. Coming up from the bottom, we'll come up to this open dot here at -5, and then we'll go up to this closed dot at -3. So that's the first part of our range. we can see that there's clearly going to be a gap after this, so we need an interval right here. -5 parenthesis to -3 bracket. All right, union, let's keep going until we reconnect with the graph. And that happens right here at -1. Now let's keep going, We'll go to the next place of interest, which is at this open dot, but don't be fooled. The graph is defined over here. We're in the range. We may not be in the range at this open dot. This part of the graph takes care of that. So we've not lost contact with the range. Keep going to our next point of interest, which is this open dot. And again, that open dot right there would imply that we're not making contact, but you got to think beyond the graph here. If I zoom out a little bit, we're making contact right there. So despite this open dot, we are still in the range of this function. Going up into the next point of interest, which is this open dot, you get the point now. These open dots are meant to trick you, to mislead you, but the graph has been making contact with this line all along. So we have not broken the range. Keep going up, and we will see that this function, just as it extended infinitely right, is also extending infinitely up. So there's no upper boundary, and this right here covers our range. So this portion right here is boxed in. The top portion of this graph just has a lower boundary. So we'll see that right there. That's two intervals. We have our first union. Our second interval is -1 with a bracket to infinity. Just like this. So despite this function having 3 different pieces, I've mixed and matched the closed dots and the open dots and in such a way that the domain and range only required 2 intervals apiece. So hopefully that fascinates you, intrigues you a little bit. Again, if you want to see how I typed out these piecewise functions, you can click that Desmos link in the description. Okay, we've made it to the 4th piecewise example and the 16th, the last example overall. My goodness, I've been sitting here for a long time. Let's scan from the left. We first hit the graph at -7. That does make contact. Continuing, we will lose contact with the graph at a vertical asymptote at x equals -4. So there, again, if I zoom out and I go down here, and I zoom back in really far, you're going to see a gap there. That's how asymptotes work. So let's go ahead and write an interval for the first part of our domain. This is -7 to -4, but we have contact with -7. We don't have contact with -4. So bracket on the -7, parenthesis on the -4. Go ahead and tag on a union symbol. We'll clear this gap until we reconnect with the graph at -2, making contact. And we can go across this piece until we lose contact at +2. So the middle portion of our domain is -2 to 2, both making contact. So we put brackets on those. And then we have one more piece here. Let's clear this gap until we hit our second vertical asymptote at x equals 4. And then scanning across until we reach the end of this graph at 7. So this last piece is 4 to 7, parenthesis on the 4, bracket on the 7, with another union symbol in between those. And there you go. Here's your full domain with 3 intervals. And we can see all 3 pieces right here. And each of these 3 pieces is boxed in on the left and the right individually for our 3 intervals. For the range, coming up from the bottom, we're already in the range of this function, so let's just go up to the first relative max, which is at 1. Both of these ends make contact with 1. I can click and get dots. I can get dots on that, so we're making contact. There's no lower boundary here, right? If you zoom out, you're gonna see that this graph extends infinitely down. So the first interval for our range is -infinity up to 1 with a bracket on the 1. Union, let's go up to the second piece. We'll cover this gap and reconnect at 3. And then we'll reach the absolute maximum of this graph at 5. So at -3, this piece makes contact. At 5, it also makes contact. We can click and get that maximum up there, as well as these relative minimums right here. So those all make contact. So our second interval for the range is 3 to 5 with brackets. So we don't have a lower boundary. We do have this upper boundary with a gap and another lower, another upper. And here we can see that animated. There you go. You got it all boxed in as much as you possibly could. So here we had 3 intervals for the domain with a mixture of brackets and parentheses. We had 2 intervals for the range, also with a mixture of parentheses and brackets and a negative infinity on that range right there. So good. That was a solid example.